Pradeep Tapkire, sir, Head of Department at NB and SCOE Solapur, who have successfully guided multiple doctoral candidates and continues to influence the academic discourse through this work. I hope Pradeep Tapkire, sir, are you there?
Yeah, good evening, ma'am.
Good evening, sir. Thank you so much for being a part of our today's session. Over to you, Pradeep, sir.
Yeah. I hope my screen is visible. My screen is visible.
Yes, sir. Yes.
Yeah. Thank you. Good evening to all. It's a very nice discussion done by our dear faculty member, Jain sir, regarding engineering mechanics. He reshaped the entire concept of friction and equilibrium part. Now, continuing with the next part of structural analysis, that is solid mechanics. Particularly, as per the syllabus of GATE, we have solid mechanics part which is connected to bending moment, shear force, and statically determined beam, simple stress and strain relationship, simple bending theory, flexure and shear stresses, shear center, uniform torsion, transformation of stresses, and buckling of column, combined and direct bending stresses. This particularly a part of solid mechanics which is normally connected to the second year level curriculum of universities or autonomous colleges, which is basically part of basic structural analysis. Now, today, as it's a demo part which is required to be put up in front of you, I focus on bending moment and shear force in statically determined bend. Basically, after graduation also, because shear force and bending moment, these are the two concepts which we require not only in analysis, but whenever we are going for design, basic part is that we need to work on the bending moments and shear force, and accordingly, we need to go for either it is steel design or RCC design. We require these two concepts throughout the entire curriculum of civil engineering. Now, what is shear force and what is bending moment? Before that, we need to answer the one question, that is, what is beam? Always we are trying to define the beam in a different way. Probably you might be define the beam in a different angle, but the structural member which is subjected to transverse loading is called as a beam. Right now, the beam basically we are looking towards the structural member which is not like always a horizontal member. It can be an inclined member as well. So when we are saying that shear force and bending moment, how that particular concept is worked out? Let us work out the internal forces which is there on the which is generated in the cross section when beam is loaded with internal forces are developed, which are trying to maintain the equilibrium. Now, equilibrium means what? We are considering the beam as an example of equilibrium, right? So these internal forces which are getting generated, they are either in the two form, that is, one is shear force in vertical direction and normal force, normal to the cross section in the direction of axis, that is the longitudinal axis. There are three axes to the member. One is longitudinal. Longitudinal means along the long directions. The beam is a member where the longitudinal axis is along the length and other two dimensions are less as compared to the length. So these internal forces which are developed, there is shear force in vertical direction and normal forces in direction of axis. Now, in case of sagging, what happened actually? The top fiber of the beam, which is getting compressed, which is getting shorter, and the bottom fiber of the beam, which is getting elongated. Well, that means which is getting which is get stretched. So top of the beam gets shortened, and so the normal forces in the top of the beam is in compression. That is what we are trying to put up our maximum concrete part in the RCC member. So above the neutral axis, the part which we are mentioning is a compression over the, because at the neutral axis what we are assuming that there is a zero stress. At bottom of the beam gets elongated. Similarly, the normal forces in the bottom of the beam will be tensile. So the normal tensile and compressive forces equal to the equal in magnitude, and hence whatever these forces, if we work out the resultant of these compressive force and tensile force, it is just equal and opposite forces, and which are trying to develop a resisting couple, right? So the normal forces to the cross sections are generating the resisting movement, and that movement, that means the next part is that this means internal forces acting on a beam section can conveniently represented by two resultant, that is, one is vertical component of internal forces, which we called it as shear force, and normal component of internal forces, which we are containing which we are converting as a bending moment. So in other words, shear force, it is a net unbalanced force in a single line, because uh, I saw a number of batches getting passed out from civil engineering from various institutes, right? After getting completion of graduation, also we are not able to define the shear force. This is what the true story. But shear force, it is a single line definition which we can say. What is shear force? It is a net unbalanced force at that particular section. And what is bending moment? It is a net unbalanced movement at that particular section. That's why it's a single line, four words definition. Net unbalanced force at the section and net unbalanced movement. Now, before going for the examples, this is just a quick revision of what we know as a loading. So we know the concentrated load, we know the distributed load. In the distributed load, that is the uniformly varying distribution is also there. Then movement, concentrated movement. Then in support, there are different types of supports as the considering the uh, beam as a part. Pin support, then pin is having the two different reactions. One is horizontal and one is vertical. Roller is having the only vertical reactions, and fixed supports is having the movement along with horizontal and vertical reaction. Now, what is shear force and bending moment diagram? This is what the variation of shear force. If we go on taking the sections from one support to other support, then what will be the unbalanced movement at every section? If we are trying to represent that particular value in the form of graph, the whatever variations we are getting, that variation is nothing but shear force diagram. Similarly, if we work out the unbalanced movement at every cross section of the beam from one support to other support throughout the length, so whatever that variation is getting, if we try to plot that variation, that is nothing but the bending moment diagram. So there are three steps which are there. Draw First, you have to draw the free body diagram of the beam. Then, of course, as sir mentioned earlier in the mechanics session, that we have to work out the equilibrium of the beam, and then we have to find out the reaction and reaction moments if it is there. Then, of course, these are the three equilibrium equations: Fx, summation Fy, and movement. Then determine the shear force and bending moment at a particular section along the beam. Now, general sign conventions which are used uh, particularly for defining the shear force and bending moment. These are sign conventions varying according to the conceptual. Sign convention, let me tell you, sign convention is for our convenience. If somebody is taking upward positive and somebody is taking downward negative, that doesn't mean that somebody is taking upward negative and downward positive. That is, the thing is that sign convention is for our convenience, definitely. We need to understand the sense. in which unbalanced force is active. Similarly, we need to understand the what is the sense in which whether it is a clockwise movement is unbalanced or whether anti-clockwise movement is unbalanced at that particular location, at that particular section, that particular part which we need to understand, and accordingly we can uh, define the sign convention. Once this, see, maximum times what is happen, the jumbling is happen in this particular part of calculation, that is defining the sign convention, right? Sagging movement which are normally considered as positive and hogging movements are considered as negative. Let us take an example. It is a simply supported beam. I'm just taking a simple example. I'll show you the some get one or two examples of uh, which are occurred in the previous gate examination. For just explanation of this particular demonstration, I've put up the simple example of 2-point load 50 and 6 kilonewton at 2 meter span each. Right now, if we work out the reactions, so it's the if I take summation Fy, so Ra plus Rb is equal to 15 plus 6, 21, right? If I take the summation of movement at B, then Ra into 6 plus 15 into 4 and plus 6.6 into 2. So this is together Ra is worked out to be 12 and Rb is worked out to be 9. This is what the very first step of our uh, shear force and bending moment calculation. Now, if we take a section in between first left reaction and first just right first left part of 15 kilonewton force, in between reaction and just left of first force, what is there? There is only one force, that is 12 kilonewton, which is upward, and there is no another force. That means there is an unbalanced force of 12 kilonewton which is upward. Similarly, whatever movement created by this 12 kilonewton force is the only unbalanced movement up to just left of 15 kilonewton force. Now, you can see in the diagram, shear force is up to 12 and bending moment is 12 into 2, that is 24. This is up to any section in between left to just left of 15 kilonewton. Once the section line is crosses 15, then 15 kilonewton force getting added. So 12 is upward, 15 is downward. So what is remaining is minus 3 downward. That 3 is downward. That means as downward we are considering negative. So 3 is downward. So at the 15 kilonewton, if we cross the section line to the 15, what will happen? So minus 3 will be the shear force. So from 12 to minus 3, the shear force line you can see. And then again from 15 to 6 kilonewton, what will be there? There is no any another force which is getting added. So 12 is upward and 15 is downward. This is the combination which remains constant up to 4 meter, just left of 4 meter or just left of 6 kilonewton. Now, when what will happen? Just you can similarly work out the what will happen with the bending moment. 24 kilonewton meter is the bending moment. Now, what is the bending moment? 12 into x plus 2. If I consider x from 15 and 15 into x, that is what the part which is there. Either you can consider x from left or x from the considered point. So 15 in 12 into x plus 2 minus 15 into x, that is works out to be 18 at 4 meter or 2 meters from 15 kilometers. So again, I am from as I mentioned in the previous slide, you have to just work out, just concentrate on what is the net unbalanced force at that particular section. Similarly, for shear force and bending moment, these two definition has to be fixed in your mind, right? Once these definitions are fixed, whatever the question is there, according to that questions, we can just check out with the concept, whether it is unbalanced force or not. That's all. Moving to the next part, that is last part, last 2 meters. Once we cross the cross section, what is there? Now, if we consider the left side of again beam, then unbalanced force is 12 upward, 15 downward, 6 downward. 15 plus 6, 21, 21. is downward and 12 upward, so what is remaining is 9. So minus 9 is the unbalanced force when the section line crosses 6 kilonewton, which is just right of the 6 kilonewton. Now this combination remains same up to second support or right hand support. Now similarly, 12 into x plus 4, if we consider x from 6 kilonewton, 12 into x plus 4, 15 into x plus 2 and 6 into x. If this is the part which we'll consider. Now you will find that this summation at x equal to 2, the summation will be 0. X equal to 2, 12 into 6, 15 into 4 and 6 into 2. So which will comes to be 0 because this is a simple support, and at this end, at the support, the bending moment should be 0. And this is how the bending moment diagram can be worked out. I hope everyone understanding. Is there any doubt up till now? If we don't have doubts, let us continue. What is the relation between the shear force and bending moment? This is again a little bit mathematical part, but this need to be understand. Of course, this will be this particular relation will require entire session, and I'm just putting the in one slide so to understand. Whenever there will be a continuous sessions, definitely the separate time will be given for this particular part. There is a relation between, of course, applied load, shear force, and bending moment. Now, if we consider load as a function of x, and then what is dv by dx? dv by dx is nothing but the slope of the shear force curve at a given point is equal to the minus the distributed force. That is dv by dx is equal to minus w, and slope of bending moment curve at a given point is equal to the shear force. That is what dm by dx is nothing but the shear force. Of course, the equilibrium part which is shown in the diagram, the left side is upward force, and then clockwise movement and anti-clockwise movements are shown on either side of the part of dx, which is the what we can say, this portion of a beam. Dx is the length of beam which is considered. Now, if we integrate dv by dx is equal to that, as I mentioned, slope of shear force curve at given point. So if we integrate the change in shear force between 2 points, v2 minus v1, which is equal to minus of integration from x1 to x2, x1 to first position to second position, area under the loading diagram between the 2 points, that is w into dx. Similarly, dm by dx is nothing but the shear force, that is the derivative of movement if we take, that if we integrate that particular part, there is a change in bending moment between 2 points is nothing but the integration of area under shear force diagram between 2 points, that is x1 from one position to other position. Whatever the shear force diagram, if we find out the area, that is nothing but the change in bending moment of between 2 points. And this is what the relation between shear force and bending moment. And this is what the final shear force and bending moment diagram which we can see. For the another example, just similar to that, there is another say 12 meter span beam is there, 8 kilonewton per meter UDL is there, and the point load is there at 2 meter from right support. Now you can just again see 34 is the reaction, 50 is the reaction on right hand side. Now again, just quickly, I'm not going to tell this particular part in detail. We're going to consider a few more examples in the sessions. Now 34 for first 2 kilometer, 34 kilonewton remains same in shear force. 34 into 2, 68 will remain same till the left part of UDL, just left to the UDL. Once we are entering the UDL, the equations of movement is getting changed, minus 4x square plus 34x plus 68. Now that portion is the second degree curve, which we called it as a parabola. And you can see in the shear force diagram, As it's a uniformly distributed load, the shear force diagram, the uniformly distributed load means the load is varying according to the change in length from 0 to 6 meters. Now that 0 to 6 meters change in length, with that earlier the point loads were there. Now here the uniformly distributed load there. So from this particular part, the variation of shear force is linear. Now in that first degree changes in bending moment to the second degree. This is how we can work out the shear force and bending moment diagram for different kinds of loading. Now these are the examples. This is particular example from GATE 2018. For simply supported beam of the length L subjected to uniformly distributed moment m kilonewton meter per unit length as shown in figure. The bending moment in kilonewton meter at a mid-span section of the beam is, the options are 0, first option is 0, second option is B is M, third option C is ML, and D option is M by M. Now this particular little bit tricky, but the concept is remains same. Again, it is unbalanced movement. But what is the concept is that now the movement which is given is kilonewton meter per unit length, right? So it is not only M, which is a normally which we will taking as a couple. So total movement total uh, the reactions which are worked out to be RA into RB into L, that is M into L is equal to RB into L. So L gets cancelled out and RA is remained M. So one reaction is going upward and another reaction is going downward. So the reaction is not M by L. So reaction is M. Now if reaction is M, then bending moment diagram which we can see in the right side part of the slide. Then if we take the section at a distance x from left support, what we can see at any point or any section, what is unbalanced movement? RA into X, that is M into X minus M into X, because M is again function, M is per unit length, kilonewton meter per unit length. So total movement will be M into X. So RA into X minus M into X. So M into X minus M into X. That becomes 0. So answer is A. So this is what little a short tricky question, but definitely this can be worked out with the help of the concept which we have seen, that is a unbalanced movement and unbalanced force at that particular section. Now another example from another uh, GATE exam, that is consider the three prismatic beams with the clamp support P, Q and R shown in the figure. Now first is a cantilever with 80 Newton force at the free end, 8 meter span. Again, Q is the prismatic section, again 20 Newton per meter, 8 meter span, again it is there. And then R is another beam. Now given that the modulus of elasticity is equal to 2.5, of course 2.5 into 10 raised to 4 MPa, and the moment of inertia of I is equal to 8 into 10 raised to 8 mm raised to 4. The correct comparison of the magnitudes of the shear force S and bending moment developed at the support is. Now this is what the part which is given. Uh, if SP is less than SQ or less than SR, MP is equal to MQ or MP is equal to MR. This is what there are four options which are given. Now what you have to do, you have to select a particular option which is as per the requirement. You have to compare the magnitudes. That is what first is 80 Newton force at the free end, then UDL, and then couple at the couple of 640. Now if we consider shear force at support SP in case of P beam, right, which is there. Now movement at support is 80 into 8. So it is a 640, right? Now, if we consider the Q, so what is movement V is at any part of section 20, shear force at support, not at any part, at SQ, the shear force is 20 into 8, 160. And what is movement at support? 20 into 8 by 2. That is, of course, because of UDL, it is 8 by 2. Then again, it is 640, right? So, and if we see last part, that is at couple, 640 is the uh, movement which is given at the free end. So, shear force at end, which is equal to 0. So, movement at support is 640 Newton meter. Now, hence, from above values of SP, SQ, SR, now what we can say, SP is less than SQ, which is greater than SR, and all three movements, MQ, MP, and MR, these are the three movements which are same in three cases. So, little bit tricky, but in this particular kind of example, you need to solve the three beams and you have to come to the conclusion. I'll just this is what the last part is, which I want to discuss in the today's demo part. Of course, other part of solid mechanics, that is simply simple stresses and simple strain relationship, simple bending theory. Of course, flexure stresses and shear stresses we're going to discuss in a depth. Shear center, uniform torsion, transformation of stresses, that particular part will be also covered in the schedule. And then last part, which is also important, that is buckling of column and combined and direct bending stresses. Around 7 to 8 marks questions are there in this particular on this particular topic. And then shear for this particular part is also important from MPSC point of view. If you just compare the MPSC syllabus, this particular part is included. And if you see the previous MPSC question paper, 15-mark question, it was there on shear force and bending moment. And a very simple beam was there. But people are not able to even work out the shear force and bending moment diagram for overhang beam, simply supported overhang beam, which was there in the previous examination. This is all about today's session. I hope everybody enjoyed this particular part. And thank you very, very much for your patience listening.